Now we are on to current. Did it actually type anything? No, I'm just randomly typing letters right now. Current. And we're going to count how many times I say so, apparently, and ah. I love so and I love ah. Like the song from... Nope, don't say it. Alright. We are going to cover current, and as per usual, straight from the syllabus, current is related to... Oh, there's an ah. Current is related to the flow of charge, and then there's a formula, so it's kind of easy. Oh, well, that so doesn't count. I'm gonna not be able to stop laughing through this whole thing. Now, flow has to do with how quickly something is moving or how frequently something goes past. So when you're looking at flow of traffic, there's two ways to tell how fast traffic is going. You can watch one car and time it to go from A to B, or you can sit on the side of the road and count how many cars go past you. Both of those methods will tell you flow. And that is how we calculate flow for current. Current is an approximation of the amount of electrons that are moving. Ooh, I should have typed it. Why don't I just type it? Electrons. The amount of electrons that are moving. And if we want to figure out how many electrons are going past and how quickly, we just divide that by the time. Now we know when it comes to electricity that electrons are telling us our charge, because the electrons are what carry the charge. So your formula for current is charge over time. Now, I tell my students all the time, the first few lessons in electricity will make or break how you understand electricity, because almost every quantity has a different unit and a different symbol and a funny name. Okay? So, like we learned before, charge is measured in coulombs. This is just review. Coulombs. And its symbol is Q. Alright? Now, current is a word, but it is measured in amperes. Oopsies, my mic is falling. Amperes. Oh, that's brilliant. And amps, but the symbol for current is actually an I. Alright, so current equals capital I. Anyway, my formula for current is I equals Q over D. And what that is telling me is how many electrons are walking past a certain point in my circuit in 1 second. So current is related to the flow of charge. Current tells us flow. And the way we look at flow in this situation is how many electrons are passing in each second, or how many charges, because technically it could be both. Alright? Use and describe the use of an ammeter and distinguish between the direction. Oh, I should probably show you what I'm reading. Use of an ammeter and distinguish between direction of flow of electrons and conventional current. Alright, so let's go into flow of electron versus conventional current. Now, when we first discovered electricity, or when we first started making circuits, we had no idea how small electrons were. We couldn't see them. So here's my basic circuit, and I'm going to put, because the line's already there, 2 fuses. Alright, this is crooked. Why is it crooked? Why can't you write straight, boy? So in your basic circuit, when you see it set up like this is my power source. The long line is the positive, because you can break it in half and make a positive out of it. And the short line is the negative. Now conventional current, so C, O, and conventional. Conventional current, oopsies, you're better than that, went from Z positive, I should make that red, and then change the other thing. Oh my god, brilliant. Conventional current went from positive to negative, right? That was what we knew current to be. When in reality, the electrons were actually going a different direction. Let's make them green. Let's call them oh, that did not come out green at all. Electrons. The electrons went in a different direction. The electrons actually go from negative to positive, which makes perfect sense because the negative part of the circuit is where all my negative electrons are hanging out. That's why that part of the circuit is negative. So they go from negative to positive. So the conventional current and the electron flow are opposites. So if you are told which way the current is going, you know which way the electrons are going. Also, once you know which way the current is going, you know where the positive and the negative are. So if I was an absolute silly person, and I erased all of this, you can tell me which side is positive and which side is negative because you know which way the electrons are flowing, because it's opposite to conventional current. Capish? Now let's get on to ammeter. Now ammeter is a device that we use to measure the current in a circuit. Now when you use an ammeter, and this is its symbol, a circle with an A in it, so it's Captain America, you put it in what is called series because you want it to count all the electrons that are going through the circuit. Okay, and it will come up with a number, 5 amps, and that is calibrated to the amount of electrons that are passing in 1 second. Of course, it's not 5. This is a calibration. Okay, so the ammeter always goes in what we call series. Think of an ammeter like a turnbuckle at a train station or at ice cream, that little thing that you walk through and it spins and it counts how many people walk in the room. Same idea. Okay, so that's how ammeters work. Plug them up in series and it counts all the electrons going through. Yeah, that's pretty much it. Let's take a peek at our thing. Current is related to flow of charge. Check. Use and describe the use of an ammeter. Check. Show understanding that a current is a rate of flow of charge, and recall the use of the equation I equals Q over T. Check. Distinguish between electrons flow and conventional current. Check. Let me just double check this ammeter point. Yeah, the textbook doesn't really say much different. They do reverse the I equals Q over T formula, and they base it on what a coulomb is versus what current is. So current is coulomb over time, but 1 coulomb is current times time, and that's because 1 coulomb is the equivalent to 1 amp and the amount of, and 1 second, sorry, drew a blank. Alright, that's that.